Hello everyone, my name is Jimmy Xiao. I'm currently a PhD student at Northwestern University. Today I'm presenting our work, Monetizing Spare Bandwidth, the case of distributed VPNs. Before going into the details, I'd like to take a moment to thank my collaborator Matteo Babello from Nokia Bell Labs and my advisor Alexander Kuzmanovich. In the past decade, the average internet speeds in the US home have grown over 20 times from 8 megabits per second to now almost 200. The trend is similar in other parts of the world. However, previous studies suggested that the bandwidth usage is not that much. This figure comes from a Wall Street Journal article back in 2019. The x-axis is the bandwidth that the user has, and the y-axis represents the average bandwidth usage. Here we can see that the bandwidth usage is less than 20% for many users, and less than 6% for those who have a bandwidth of over 100 megabits per second. So there is a lot of spare bandwidth that are wasted. Conjunction with this trend, there appear several distributed VPNs. We will later call them DVPN in short. Here, instead of connecting to a centralized VPN, that is, one out of hundreds of servers that are controlled by the same company, DVPN users connect to residential home networks of other users and use them as a relay point to the internet. And transactions are made between two individual users based on blockchain. DVPN allows the user to monetize their spare bandwidth by providing VPN services to the public. We can thus say that DVPNs are building bandwidth marketplaces, which is the topic we will explore in this study. Okay, so now let's look at the existing DVPNs. This table presents 6 of the most recent DVPNs that we have found. Marked in red are Orchid and Lithium. Lithium is already a dead project, whereas Orchid is still in development. So we ignore them in this study. Next is Privatix, marked in yellow. It does not allow seller to join, so we only measure it actively. And then marked in green are 3 DVPNs that we will focus on in this study, Mysterium, Sentinel, and Tachyon. We perform both active and passive measurements. Our active measurement rely on Android DVPN clients. We use a Raspberry Pi to automate the operations, including recording snapshot of the full list of the DVPN nodes and connecting to them and measure available bandwidth. First, we look at the number of nodes for different DVPNs. We select the centralized VPN, Proton VPN, marked in black as our comparison. We find that Mysterium and Tachyon both have over 1,000 nodes, which is competitive to Proton VPN. In particular, the size of Mysterium is increasing very fast, from 200 to over 1,000 within half a year. In the plot, it shows a temporary drop. It was not really a drop, but it was that Mysterium are switching to another version, and we stayed on the old version for some time. On February, we upgraded to the new version, so the number of nodes jumped up. Next, we look at where the DVPNs are located. Basically, they're all over the world, but as the figure shows, US or North America is where most nodes are located. Also, a lot of nodes are in Great Britain or European countries. Singapore is a popular place for Tachyon. Next, we periodically sample the nodes and connect to them and test the bandwidth. The figure shows the city of the download speed. We can see that only Tachyon nodes are overall slower than centralized VPN. Mysterium is competitive to centralized VPN, whereas Sentinel and Privatix nodes actually have much better performance than centralized VPN. Overall, these findings verify that DVPNs are competitive to centralized VPN in terms of size, geolocation distribution, and performance. We now present our passive measurement. For this measurement, we join the DVPN network with our own machine. We have 7 nodes in the US, including 5 in AWS Cloud and 2 residential nodes. We also have 1 cloud node in the UK, 1 in Italy, and 1 in China. The Chinese node did not serve many sessions, so we excluded from our results. The measurement lasted for 2 months, during which our nodes have served around 16 terabyte data from over 500,000 buyers. The total number of DVPN sessions is over 600,000. So some buyers have connected to our nodes for multiple times. That goes down to over 600 million TCP or UDP sessions, which means that a DVPN session on average have generated around 1,000 TCP or UDP sessions. This figure shows the origin and destination of the DVPN sessions. In the middle is our nodes. We can see that a large portion of the traffic comes from countries in the Middle East, where some content censorship is implemented. So some of the buyers may use DVPN because they want to circumvent censorship. However, most users are actually coming from the US. So we suppose another purpose of the buyers is to protect their privacy. With respect to the destinations, servers in the US serve most of the traffic, more than 50%, and then follows with Russia, China, and UK. But this may be biased because we find that 26% of the traffic actually went to CDN servers. Next, we report the traffic characteristics. Overall, for each DVPN, we didn't observe any statistically significant difference across different nodes. But we do find that traffic characteristics is different for different DVPNs. Therefore, we report the aggregated results from all the nodes for each DVPN. In this figure, we show the DVPN session throughput and peak throughput. The peak throughput is the maximum throughput of TCP or UDP session in each DVPN session. We can see that Tachyon has the lowest throughput, Sentinel is in the middle, and Mysterium has the highest throughput. It's a little bit different in terms of peak throughput, with Sentinel has the highest peak throughput. There is a large gap between the average DVPN session throughput and the peak throughput, which means that the buyers are idle for most of the time after connected to a DVPN node. More details about the size, duration, and volume of the DVPN sessions, please refer to our paper. Next, we report the traffic type. We first investigate peer-to-peer traffic. This is because peer-to-peer traffic is usually associated with copyright violations. In fact, during our measurement, we have received several alerts of copyright violation. We use IPP2P to identify peer-to-peer traffic, and we find that only around 3% of the traffic is peer-to-peer traffic. Still, the sellers may be faced with the potential copyright violation risks like we did if they do not block P2P traffic. Next, we rely on McAfee domain classification for both risk and type categorization. Here, unverified is not really unverified, but it refers to risk between minimal and medium. Only less than 1% of the traffic has medium or high risk, so most of the traffic is safe. Regarding traffic type, we find no traffic type is dominant. The traffic percentage of the same type may be different for different DVPNs. More details, please refer to our paper. Nevertheless, the current DVPNs except Mysterium did not provide proper traffic control scheme to the users, and hence expose the user to any risks. We further explore the DVPN marketplace with respect to the economics. First, we look at the buyer's cost and then the seller's income. Last, we comment on the value of spare bandwidth. This figure shows the prices of all sellers relative to the lowest price for each DVPN. For instance, let's look at the red solid line for Mysterium. The minimum price per gigabytes for Mysterium is 0.01 MIST. A relative price of 20 means 0.2 MIST per gigabytes. Sentinel and Tachyon only charges by amount of consumed traffic, but Mysterium charges for connection duration in addition to that. As we can see from dashed line in this plot, it represents the price per minute of connection. But for the sake of simplicity, we will ignore the charge for connection duration in later slides. From this figure, we see that the cost for connecting to the same DVPN may vary at most 100 times, but most sellers just choose the default price. For instance, for Mysterium, it's 0.22 MIST, which is 22 relative price, and for Sentinel, it's 50. Overall, Mysterium is the most mature marketplace because first, it is where the most sellers did adjust their price setting to non-default values. And second, during the period of time of our measurement, Sentinel and Tachyon does not pay the sellers, nor do they show the price in the client's app. So in the following discussion, we will focus on Mysterium only. We'll now present market capacity. The figure shows the relationship between the number of concurrent buyers and the prices that users need to pay. For this analysis, we assume each buyer requires an average bandwidth requirement according to our passive measurement. As the load on the marketplace increases, new buyers are left with more expensive sellers, and thus the bill will go up by 70 times at most. The cost increases faster in countries with overall less bandwidth for sale. For example, 100 buyers are enough to force new buyers to pay 0.7 MIST per gigabytes in Singapore and Australia, while the US can support up to 600 concurrent buyers before reaching such high price. Next, we'll look from the seller's perspective. We propose a model to optimize the seller's income as shown in this objective function. The objective here is to adjust the price setting and bandwidth limit to maximize income with various constraints. One of the constraints is data cap. For details for the modeling, please refer to our paper. We further conducted more passive measurement to approximate the expectation in the objective function. We now present our results. We set up different machines with different price settings. As you can see in the figure, each black marker represents a data point. As the price increases, the number of daily DVPN sessions that the node serves, which is the y-axis, decreases. This is within our expectation, but the figure also shows the relationship between the unit price and income expectation is non-linear in yellow line. So there is an optimal price at 0.02 MIST per gigabytes. When the price is high, our fitting function is not so good. This is because the number of sessions are too small on average, but has very high variance. The optimal is actually different if we have different bandwidth limit. More details, please refer to our paper. Now we look at how the sellers are setting their price over time. Note that here, Mysterium has a major update in March 2021, so the default price changes from 0.1 to 0.22 MIST per gigabytes. More and more buyers are choosing a non-default price overall. Half of them set a cheaper price, whereas the other half set a higher price. But this is far away from optimal price. This shows that the sellers actually do not have any clue on how to set the prices. Last, we comment on the value of spare bandwidth. According to our modeling and measurement, we find that the sellers are receiving on average 14 cents per gigabytes a day, and the buyers are paying 11 cents per gigabytes. So we conclude that the value of spare bandwidth in today's US marketplace is between 11 and 14 cents per gigabytes. However, both the buyer's costs and the seller's prices are far from optimal. Also, it is noteworthy that the income of DVPN providers are heavily influenced by the value of cryptocurrencies that are used in the transaction for each DVPN. So the income might increase or decrease by several times within a month. Also, the value of cryptocurrencies might make one DVPN more profitable than the other from time to time. So all these observations motivated us to build what we call Ring. Ring is a concrete tool with 4 goals. First, we want to ease the use of DVPNs. The interface for different DVPNs are quite different. From our experience, it took efforts to set up the DVPN nodes. So we hope Ring would help with that. Second, we want to enable the sellers to join multiple DVPN marketplaces at the same time. And following with that capability, we want to maximize the seller's income among multiple marketplaces. Last, we want to provide the sellers with the capability to have fine-grained traffic control to protect them from any risks. Please refer to our paper for more details of the system design and heuristic design to maximize a seller's income. Our results show that Ring can help to increase the node revenue by 63%. In summary, our contributions are as follows. We present the first measurement study on the DVPNs and find that they are competitive to commercial centralized VPNs. We find that DVPN is a concrete example of bandwidth marketplace. It follows that we formalize the bandwidth monetization problem in such marketplace. We conclude that the value of spare bandwidth in the US today is 11 to 14 cents per gigabytes, but the marketplace is far from optimal. We built Ring, a multi-vendor bandwidth marketplace, and a heuristic to optimize the income for the sellers. Other potential work may include to have a deeper theoretical analysis, for instance, use a game theoretical model. This is all my presentation today. Thank you for watching.